First stated objective here is Stefan Boltzmann versus insulation. So, if we're going to talk about Stefan Boltzmann versus insulation, what we really want to talk about is energy and equilibrium temperature. Right. So the first law of thermodynamics is energy is neither created nor destroyed, only changed from one form to another. So in any situation that you're dealing with energy, it has to be conserved. If we have an object and we have some energy going into it, that energy must equal the amount of energy that is leaving that object, plus the change in internal energy. So let's imagine that this is the Earth. A thermodynamic system can be defined in any way that's useful to us. So let's define the Earth as a whole thermodynamic system, in which case the energy that's entering the system is the energy from the sun. And that's in the form of electromagnetic radiation, infrared radiation, ultraviolet, visible light, which carry energy with them. And if you want to look at it from a quantum perspective, they are photons. And the sun emits a hell of a lot of this stuff. The Earth gets something like 1/1000% of the sun's total power output. So we have this energy coming in. And then we also have energy leaving in the form of electromagnetic radiation, which we kind of colloquially say is the Earth giving off heat into space. And this is described by something called the Stefan Boltzmann equation. Now, the amount of energy that's entering the system has to equal the amount of energy that is leaving the system. Otherwise, there is a change in the internal energy. What that means, just to pare down the thermodynamics, is if the amount of energy from the sunlight is greater than the amount of energy that's leaving, as described by the Stefan Boltzmann equation, then the total amount of energy in the system is increasing. And if that happens, if sunlight is greater than the Stefan Boltzmann radiation, then there is an increase in temperature. So there's like an exchange rate between energy and temperature within a system, which is defined by what's called the heat capacity. So this is that's like kind of thermodynamics 101, this idea that you have energy that isn't created or destroyed, you just change it from one form to another. So let's write an equation, right? So let's say that we have some amount of energy coming in from the sun, S. And in equilibrium, that is to say like the steady state where nothing is changing inside the system, this equals the Stefan Boltzmann radiation. And that we can write an equation for in terms of the temperature of the system. So the Stefan Boltzmann rule is basically a way of saying the hotter something is, the more energy it gives out. And so we can define that with a physical constant, the Stefan Boltzmann constant, multiplied by T to the 4th power. So that means that if you increase temperature a little bit, suddenly the thermodynamic system gives out way more energy. So this is the equilibrium state, okay? But if we were to put this on the other side of the equation, so it's the difference between these two, the incoming energy from the sun, which I'm just writing as S for the time being, which we will assume to be constant for this project until we don't, minus the energy output of the Earth. And the other thing to note is I am basically simplifying this down so that now we're considering the amount of energy that arrives from the sun over 1 square meter of the Earth. And then this is the amount of energy radiated out by 1 square meter. If we wanted to make it so that this is the total energy incident on the entire planet, then we'd multiply this term by the surface area of the whole planet. So the difference between these two is then the change in internal energy, which in thermodynamics you normally would write as delta U, like that. Just a slight tangent here. I really love the Stefan Boltzmann constant, because the Stefan Boltzmann constant is one of those few times where nature is like actually nice, and this thing, the magnitude of this is 5.67 times 10 to the minus 8. 5, 6, 7, 8. 5, 6, 7, 8. No reason that should be the case. I just think it's pretty neat that it is. So that imbalance in energy is the change in internal energy, and as I said, there's like a exchange rate between change in internal energy and change in temperature. So if I write this out again, so this is for 1 square meter, the imbalance in energy equals the change in internal energy, which I will now write as a heat capacity, the exchange rate, multiplied by delta T. So the change in temperature. Now, that is that equation is basically what we're going to be working with today. Which heat capacity. So this is basically how much energy you have to put into 1 square meter of the landscape to increase its temperature. So it's the formal definition would be if this was for water, for example, if you had 1 kilogram, beg your pardon, if you had just 1 liter of water, the heat capacity of that water is 4,200 joules per Kelvin, meaning that you'd have to put in 4,200 joules into that liter of water to raise its temperature by 1 Kelvin or 1 Celsius, completely equivalently. So Thunderstorm's asking a question there, is that specific internal energy? Specific internal energy refers to the internal energy per unit mass. If something is specific, at least in this context in science, it means per unit mass. So what you'll sometimes see is lowercase c will be the heat capacity of an object per unit mass, so like per kilogram of water. Or sometimes you will see capital C, which will be the heat capacity for the entire object. In this case, we're fudging it a little bit in the stream because we're basically going to assume a vague heat capacity which is associated with like the top layer of the ground. Obviously the heat capacity of the whole planet is fucking enormous. We're just going to consider the bit that's thermally accessible to, the radiation from the sun. So the top little bit. So we're really close actually to having something which we're going to then represent in code. So what we have here is change in temperature as a result of an energy imbalance, right? Now, if we change this from being an amount of energy, because right now this is energy, and let's say we're interested in the energy per unit time, so the amount of energy that arrives every second, because that's what we normally like to consider in physics, right? This is going to be the final version of this equation that we'll write out. So the change in temperature of a thermodynamic system over some time period, let's call it lowercase delta t, is going to be lowercase delta t, our time difference, multiplied by the energy imbalance, so S minus Stefan Boltzmann energy, divided by the heat capacity. Now that may look really complicated, but to be honest, it's really not. It's just, if you want to increase, or if you want to change the temperature of an object, the longer you spend trying to force it, the bigger the change you'll see. These two are in proportion to one another. The more sluggish it is to responding to changes in temperature by when we force it with energy, the less change in temperature you'll see. So for a given amount of energy that you pump into it, the bigger its heat capacity is, the less temperature change you'll see. And the more energy you have going into it than energy leaving it, the bigger the temperature change you'll see. So it's in direct proportion to the energy imbalance over the object. So if you don't follow the equation, just remember that this kind of makes sense, right? That the longer you spend forcing this thermodynamic system, the more change you're going to see. The more responsive it is to that change, the bigger the response you'll see over that time. And the more you pump the system, the bigger the energy imbalance, the more change you see. That's basically it.